Hi, Wayne Prentice here. Thought I'd do a revisit of a talk I gave a couple of weeks ago. We had some good discussions afterwards, and I got some feedback by email, and I thought I'd talk about it here. During the video, I made a claim about depth of field, and I think I might have left everyone with the wrong impression, including myself. So I thought I'd go over what I said, add some content, and leave it right there. A very short video today. So last time I said the depth of field can be controlled mostly by F number, because if you controlled for the subject size in an image, for example, if you had a 50 millimeter lens and you were 4 meters away, you'd have a certain subject size. If you took the same image at 8 meters away with a 100 millimeter lens, you'd have the same subject size. You'd also have the same depth of field. And during the discussion, we talked about a couple of things that made you want to consider other things in depth of field when selecting focal length. And that's what I want to talk about here. Two things came up. The first one was when selecting a focal length. Aesthetically, there may be a reason to select at a wide angle versus a telephoto. And the reason being because of the field of view. Again, controlling for the subject size, if you have a wide lens, you get a more of a surround. You have a wider cone behind the subject. If you want a narrower cone, you can use a longer focal length. So beyond depth of field, certainly picking focal length has an impact on the composition of the image. Another thing I think got confused, especially by me, is that if you had a constant depth of field, that you also had the same blur in the background. Turns out that's not the case. As you can see, the blur in the background here is much more than the blur here. And so I did some modeling, and here's some modeling of a lens in the same type that was taken of this picture, and that happens to be a full frame DSLR taken at f4 at various focal lengths. In each case, the camera was focused at a point 25 times the focal length. And this plot here shows the amount of blur or defocus when you move off the plane of focus. And so to the left are points closer than the plane of focus, and to the right are points further away. If you look at the plot, you can see that the longer the focal length, the more blur that occurs. And so the amount of blur, as you can see in these pictures and on the plot, the amount of blur increases with the depth of field. So how can it be true that the depth of field can be the same, but the blur be different? Well, if you zoom into this area right here, and that's this plot region right here, over the small range of variation, the difference in depth of field is none. It's the same for the various pictures. So that's something I believe I was misleading on, suggesting that the blur and the depth of field were the same. Earlier, we looked at what the blur diameter was as a function of distance from the plane in focus. So P was the distance from the camera to the plane in focus, and Z was the distance at which we measured the blur. So let's look at blur at infinity. In that case, Z goes to infinity. This term goes to 0. So now I have this expression times 1 over P. And if we simplify that, the P's cancel out here. D is the focal length divided by the F number. Substitute that in. Now if we assume that the distance to the plane in focus is much greater than the focal length, which makes sense because P is typically in meters, and the focal length is typically in 10 to 100 millimeters. We can make that assumption. So that all simplifies down to this, focal length squared over the F number times the distance to the plane in focus. And I mentioned earlier it's a linear relationship, and when we plot it, we can see that it is linear. So the takeaway here is that the amount of blur we get can be described easily by this. You can notice it's a linear relationship, and this suggests it should be a squared, The reason it's linear is because we're maintaining the subject size. So as a result, the plane in focus is 25 times the focal length. So P here is 25 times focal length. That puts the focal length in the denominator into focal length squared, which makes it linear with focal length. So the takeaway here after all this is to say that when you maintain for a constant subject size, the blur in the background and infinity increases linearly with focal length, decreases linear with F number. However, the depth of field remains constant. So despite a constant depth of field, there is a difference in blur in the background, and this equation describes that blur. So that's all I have today. We'll look a little closer. So here's a set of images taken over a range of focal lengths. In this case, a very wide focal length, and you can see that in all cases, the subject is about the same size. And here again, to repeat, there's a much larger field of view behind the subject, more surround, compared to here, which is a narrower cone, and that the objects in the distance are much clearer than they are here. So I hope that clarifies things. My apologies for not being more complete in my explanation, and I really appreciate the feedback, and thanks so much for watching. Take care.